Hi, I'm Carlton Coffrin.
And I am Lina Roald, and we are going to talk to you about the use of convex relaxations in power system optimization and give you an introduction to the little series of presentation that we have made for you on this topic.
So the first big question is, why are we making this collection of videos? And the main motivation for us is that we want these presentations to be available for a past version of ourselves.
So kind of what would have helped us understand relaxation in power system optimization better as we started out working on these topics.
So the scope of these lecture series will primarily give an overview of the core concepts in power flow relaxations. We're not going to go into a lot of details of any specific relaxations. That's better left for a literature review or another series entirely because there's a huge body of work to cover. But what we're really going to focus on here is the big concepts, so that makes it easier if you pick up one of those papers to be able to follow it.
Yeah. Yeah, and the intended audience for these presentations is thought to be undergrads or early grad students in power engineering programs, so people who are working on power systems and want to use optimization and relaxations in their work, or maybe work on making better relaxations. And then we also intend this to be accessible for undergrads and early grad students in computer science and operations research programs who are looking at power engineering applications.
And I think it's important to mention there, because we're trying to hit both audiences with a kind of core base of knowledge, there's going to be times where you're going to be bored during sections of these lectures. So there will be times when we'll cover very basic power engineering things. There'll be other times when we cover very basic CS/R things, and it's because the other people in the audience will need to be learning those things. So expect that to happen, and we've broken the videos up into smaller chunks so you can skip ahead of the sections which maybe you're already most familiar with.
Yeah, and we are not going to assume any large amount of pre-knowledge. We assume that you have some familiarity with complex numbers, that you have done some high school math. We are going to introduce power systems very briefly. And we are going to introduce optimization actually even more briefly. But we will provide references on where to look more if you need to read up on these topics in addition.
So here's a basic overview of all the lectures we're going to cover in this series. The lecture we're in right now is the preliminary lectures. Then we're going to talk about AC power flow, AC optimal power flow. We'll touch briefly on what computational hardness is and what it means for optimization methods. Then we'll cover methods for solving nonlinear optimization problems. Then finally get into relaxations of optimization problems, applications of those relaxations to AC optimal power flow, and last but not least, tips for using these relaxations or developing them in your work.
Yeah, so that is maybe one thing, like kind of a list of things that we think are important for you to know and be aware of if you are doing work on this topic.
Yeah, I think the last two lectures are really what we want to get at, but all of this other stuff is kind of building up to, so you have all the background knowledge to understand the key messages of those last two lectures.
Yeah, so if you think you have seen this before, you can skip ahead and try and see it, and then go back if you feel you need to.
Additionally, there'll be a couple of bonus lectures. So I'm preparing a lecture on optimization-based bound tightening.
And I will give a lecture on how we use relaxations to solve robust optimal power flow problems.
And in time, there may be many other bonus materials that appear. We'll just see how that has to go.
Yeah, maybe if you have a paper, which would be a good bonus material, and you want to share in a presentation, feel free to do so.
So without further ado, I think we should get started on the preliminaries and notation.
Yes, okay. So then I will go ahead and I will give you a short introduction to what is a power system, or more specifically a power transmission system. So when we talk about power systems, we tend to talk about the connection, or like a power system really has a lot of different pieces to it. So on the one hand, we have power generation, on the other hand, we have power consumption, and the transmission grid is really what is connecting those pieces together. So the power transmission, the main task of it is really bringing power from generators to consumers. Recently in power systems, there's been some kind of big changes that are driving a lot of the research that is done in this area. For example, there has been a large rise in the amount of distributed generation, such as rooftop solar PV or small-scale wind generation. There is also a lot more large-scale renewable energy generation that are connected to the grid. So this really is kind of a game changer, because these types of generation are harder to predict what they are going to, how much power they are going to produce, and they behave differently than the large power generators. On the other hand, there has been a shift towards liberalizing energy markets. So we see a lot more long-distance energy trading these days than we used to. And this is changing how the grid is being used, because really the grid was meant for this original transmission of power from generators to sort of close by consumers, whereas these days energy might be traded across continents. Like, for example, in Europe, you might have people in Spain who are buying energy from coal power plants in Poland, or from the north west of the US might sell energy down to California. So there are kind of large-scale transmission going on. One thing that is sort of important to be aware of when you look at transmission systems is that there are different pieces to it, also the transmission system itself. So for example, we have the transmission grid, which is a high voltage long distance transmission of power. And you might have seen these towers around you. On the other hand, we have the distribution grid, which has typically lower voltage and only transmit power over shorter distances. So in this lecture, a lot of what we are talking about in power system optimization traditionally have been more applied to transmission grid operation, where optimization plays an important role in market clearing and secure operation. Increasingly these days, optimization is being applied also at the distribution grid level, so there is research going on in that area. And in distribution grids, actually AC power flow representations are typically more important. Okay. So if you look at the transmission system in the United States, it is a really big system. So you can look at it here. It has a continental scale system. There are very many different pieces, many different lines that connect many different regions. And even if you zoom in on some little region or smaller region, you will still see that there is a lot of complexity. There are many transmission lines, many generators, and many things to take care of. So modeling this mathematically and being able to optimize the operation of these systems is really challenging. And what we are looking at here is still the transmission grid, so you could zoom in even further and get down to even more complicated and complex representations of this system.
Do you recall this anecdote that people make often, that power systems are like the biggest engineering system that has ever been made by humanity?
Yeah.
Yeah, I don't know. People say that. I don't know if it's been
know.
really studied, but it's big and really complicated.
It is really big, and it is super important. When you look at it, I mean, you think about what would we do without electric power today? That would be sort of a disaster, right?
Yeah.
So we want to safeguard this system and make sure it operates in a way that is economically efficient and secure, so we don't have blackouts and we can keep charging our smartphones whenever we need to. Okay, so here are a couple of transmission system engineering texts that are kind of typical works that you might want to look at if you feel that you need to read up on these topics. And from there, I'm just going to head into foundations of alternating current systems. So as I mentioned before, I mean, we have this, like our power systems today are these big structures, and the power that is used everywhere, essentially in the world, is alternating current systems. So you will see when you look, if you go on a road and you look up at the transmission towers, you will see that there are typically 3 conductors that are on each towers, or there might be 6 conductors, but there are seldomly, on big transmission towers, there is usually always a multiple of 3. And that is because what we have are 3-phase systems, and there are many things about those systems and how they can be represented as single equivalent systems and so on and so forth that we are not going to go into here at all. But I still wanted to kind of give you a little bit of a flavor for why we represent power the way we do and tell you what is a phasor representation. So if you think about this, what you see on this slide is that you see a current that is following a sinusoidal curve over time. So it is varying with a certain frequency. So it's the I of time is equal to the sinus of that time. And the power system convention here, by the way, is that I is used to represent currents, whereas j is used to represent imaginary numbers. So j is essentially equal to the square root of -1. And sometimes in our slides, for the purposes of this presentation, sometimes we will also use bold I to represent the imaginary number, which is kind of the typical convention that is used in math.
And that's because as a computer scientist, I came more from a mathematics background, so I'm just used to using I for imaginary components.
Yeah, so when we made those slides, I always used J and Carlton would always use I, so hopefully we have not created much confusion here. We will see. Okay, so if we go ahead and we think about the sinusoidal current, you could also think, I mean, when we looked at it first, we had this curve, the black curve here, which is crossing 0 at time 0. But you could also think about the current having a kind of a phase shift, which is such that it crosses 0 a little bit later or a little bit before. So this would be the purple curve. And that is, I mean, representing those sinusoids can be done using a phasor representation. So for example, what you see here is a phasor. And if we represent that if we look at that in the polar form, what you see is that we have a number which is equal to the magnitude. So that is essentially the length of this little arrow that was turning around. And we have an angle, which is essentially the angle between the x-axis and the where the arrow is at time 0. So that is what we call a phase shift. Now we can also represent this sinusoid or this polar form in what is called a rectangular form by a complex number. So we can think about x here as being the intercept between the when you project this arrow down on the x-axis, and the imaginary part as being the arrow projected onto the y-axis, which would give you the rectangular form of this number. And the connection between those two is, as you can see here, with cosines and sines. So this is sort of important. When we are talking about power, we are going to use complex numbers. These complex numbers can really be any of those forms because they are equivalent, but typically we either think about them, I mean, sometimes we will think about them in rectangular form, sometimes in polar form. Okay, so this time now, so what we have really come to now is that we are able to represent this current on that figure as a timeless oscillator. So it's sort of the real part of the current plus this imaginary number times the imaginary part of the current. So these are sort of it's a concept we have made up, but it will be very useful for our further analysis. So just to also make it clear here, capital letters in these presentations are going to represent complex numbers, and lowercase letters are going to represent real numbers. So now if we go ahead and we look at the definition of AC power, what we would have is that S, the AC power, the complex power, is given by the multiplication of the voltage, which is here again a complex number representing one of those sinusoids, and the current complex conjugate. And if you multiply those numbers together and you group things accordingly, you will get that S here is also, it's a complex number which consists of a real part and an imaginary part. And that represents actually the active power and the reactive power. And it is important here to remember that when we have these kind of equations, like we have here for S as a function of V and I, really we kind of have two equations here, because we have the equation for active power and reactive power sort of put together in one.
I think it's also worth noting at this point that in power system textbooks, both the complex form and its real parts have special names for almost every interesting quantity that you might want to measure. So that's one of the reasons why we're talking about active power and reactive power. It's really like the real and the imaginary component of the apparent power S. But you'll run into all these particular names as you're reading papers.
Yeah, and there is a lot more to this that we did not cover in this lecture, as also mentioned, which yeah, we will not go into how we get from these sinusoids and what three-phase system means and so on. But really, I mean, if you are interested in this, you are recommended to go and look at that. Okay, so just also a few more things about complex number notations. So we have said here, here already, the rectangular form, the polar form, and the connection between them. Also important to know is when we talk about complex conjugate, what is meant is really this part where we change the sign in front of the imaginary part. The absolute square is given by the expression seen here. So you take a complex number and you multiply it by its complex conjugate, and you get the magnitude of the complex number squared. And what you see here is a circle, so the magnitude of the complex number squared. Yeah, you can tell there. Okay, so
I guess that's kind of the conclusion of the very fast introduction to power systems. So now I will give the very fast, even faster introduction to solving systems of equations and power system optimization. So this is actually a good time to bring up the standard notations for equations in these lectures. So if you're given an equation like y equals mx plus b, what you'll see here is that some of the terms are going to be constants, so those will be appearing in bold, and then some of the terms will be variables or unknowns, and so those will be the standard script. So what is it to solve a system of linear equations? Usually you'll see this presented as kind of a matrix A times a vector x is equal to a vector b. But you might also see it in a more like arithmetic form like this, where you have some coefficients a times some unknowns x, and then those are equal to some constants b, and you'll have a bunch of these. So the nice thing about solving collections of linear equations is that it's very easy to do in practice. There are robust algorithms. You can easily detect if their solution exists to the system of equations. You can also show that it will be a unique solution. So they have all sorts of nice mathematical properties which make solving these systems easy and convenient. Now, if you want to solve a system of nonlinear equations, it's not so simple. So typically you'll be given a bunch of functions of some variables x, and we'll just say that they all have to be equal to 0 because we can move the constant into the function g. And here, there's no simple closed forms in the most general case. So either you have to sit there and prove for this particular type of set of nonlinear equations, this is how you derive a solution. Or you can use numerical methods like Newton's methods, and those often work well in practice to find solutions to these types of systems. But it's important to note that just answering the question, does a solution exist to a system of nonlinear equations, is not trivial. You would need to prove that on a case-by-case basis. Also, determining if the solution is unique, there's only one of them, is also non-trivial. So to help build your intuition for this, let me do a little toy example. So let's say we have these two equations. They're difficult because this cosine introduces some nonlinear structure. And you can ask yourself, is there a solution to these particular equations? I don't know about you, it's not obvious to me, but potentially you could do some clever algebra and come up with at least one solution. One example is this one, where you set x to 2.133 and y to 1.066. You can plug it in and check that it's all consistent, so hooray, we found a solution to our system of equations. But you could ask yourself, well, is it the only solution? Or, we now know one exists because we've shown one, but it's not clear how we could find the other ones. So if you look at these two functions on a graph, conveniently I selected them to be 2D so that we could plot it very easily. You can actually see that there are 3 solutions, and if you zoom out, you could kind of intuitively see that these lines won't cross anymore after these 3 points, so there are just 3 unique solutions. But I hope this illustrates that finding the solutions to systems of nonlinear equations is a lot more complex than systems of linear equations, and there can be a lot of subtle mathematical challenges hidden in there. So let's talk about solving optimization problems, which is kind of like a generalization of solving nonlinear equations. So in an optimization problem specification, you're going to be given an objective function. So in this illustration, it's f of x. And then you're going to be given some constraints which are given in the form of inequalities usually. So here you can see we have like constraint G1 and constraint G2 all the way up to Gm. And then the decision variables x will be ranging over all the real numbers. So this kind of has like a flavor with all these g functions that looks similar to solving systems of nonlinear equations. But the interesting thing here is that the inequalities allow there to be lots and lots of possible solutions. And then what you're trying to do with the objective function is to say, well, of all this big collection of solutions, which one you prefer. So usually you set the objective function to be something like the cheapest. So in power systems, it could be power generation cost. So your question is like, among all the ways I could operate the power system, what is the way that would give me the lowest cost for generating power? So I think the key difference to understand about optimization versus solving systems of linear equations is that these inequalities, which are quite fundamental to optimization, lead to many possible assignments of the variables, and then this objective function is helping you select of all of those the one that you you think is the best.
So, Carlton, you have inequalities here. Can you also have equalities?
Yes, you can have equalities in optimization functions, but they're somehow, usually you can use them to remove variables because every equality is going to remove 1 degree of freedom. So usually you can kind of like take an equality and use it to remove one of the decision variables x from your problem. But as we'll see later on in these lectures, in the power problem, it's maybe not so obvious how you could do that.
Mm-hmm.
Because if the nonlinear equations are very complicated, it's not obvious how you can use them to project out specific variables. So let's just give an example of what these kind of things look like. So here is a fairly arbitrary optimization problem I just wrote up with 3 different variables. And the first question you might ask yourself is like, okay, there's a bunch of weird constraints in here, and this very arbitrary looking objective. Is there a solution to this optimization problem? Is there any assignment of the variables which can satisfy all of the constraints? Now, the first thing I learned in algebra class was when you're trying to just guess a solution to a system of equations, you can start with 0. So if you just plug in 0 everywhere, you'll see that all of these constraints are satisfied. So that's kind of a fortunate event. But then you can look at the value of the objective function, and here the objective function would be 0. So the next natural question is there a better assignment to these variables that would get you an objective function of less than 0? And I don't know about you, but it's not obvious to me. I mean, this looks complicated and quite tricky to do, but it turns out that there is an assignment which will give you minus 1/2, and I believe that's the minimum, the global minimum of this problem. And that happens when all the variables are set to 1/2. So this just gives you a feeling for how you can write a problem using inequalities and an objective function. You can state an optimization problem, and maybe you don't even know how it can be solved, but at least you can state it in this form. So that gives us the end of this lecture. Would you like to do the recap?
Sure. Yeah, so what is it we have seen in this lecture? So first we have just tried to kind of set up the mathematical notations. We have given you a super brief introduction to power networks, what they are, what they do, and also kind of putting down the mathematics of the alternating current, or this kind of notation, the phasor notation. And then we gave you a super brief introduction to optimization.
So what's coming up next is that in the next couple lectures we're going to expand on the physics of power systems using the building blocks we started in this lecture, and then we'll derive the equations for power flow in AC power networks.
Mm-hmm.